Hey students, welcome. This is Unit 6. This is Video 1. We're going to talk about endothermic and exothermic reactions. We're actually going to cover 6.1 and 6.2, and there is no homework for either of these. Remember, if you need to read just a little bit more about it, you can read for this one in 7.2. So let's kind of just jump right in here. Thermodynamics is our study of energy of chemical reactions. So we're talking about how much a chemical reaction either gives off in terms of energy or how much it absorbs. So let's go ahead and define energy there. So we're talking about energy is the ability to cause change. So can we change something? A lot of times we have like work, we can do some movement, or maybe we're talking about a temperature change. So those two things both are the ability to cause change. We can either change movement of something or we can change the temperature. So work then is a force applied over a distance. If you remember back to physics, if you've taken physics, we've got work equals force times distance. So this has to be moving. So for work to officially be done, there has to be movement. Then we have heat. Heat is the transfer of energy from high to low. And so we really haven't used that term correctly. In terms of like our house, turn the heat on, well, we're trying to heat up the room or we're trying to get the energy to be higher so it feels warmer. But again, it's a little tough there. Okay. Then we have our law of conservation of energy. That is that energy is conserved. So we cannot create or destroy energy. This is just like the law of conservation of mass that says matter cannot be created or destroyed, only transferred. The big ones here that we want to talk about, we've got system and surroundings. System is where the reaction is taking place. So where is our reaction taking place? All right. Everything else then is our surroundings. And this actually includes everything else in the universe. So that's pretty big. All right. But that'll actually make a little bit more sense when we talk about entropy a little bit later. So we'll come back to that. Now, the two terms that we're actually really here for is our endothermic and exothermic, all right? So let's start off by defining endothermic. This is where energy is absorbed. Energy is absorbed by a reaction. So this is where the system gains energy from the surroundings. So the surroundings are giving energy to the reaction. Or this could be in terms of work, and so that is work done on the system. Some examples of this, for instance, we have our instant ice pack. These come in like first aid kits, right? And somebody gets hurt, so you pop it and it will go ahead and get cold. That's the chemical reaction right there. All right. Another one would be like dissolving baking soda in water. If you actually feel this one, it'll actually feel cool to the touch when you dissolve baking soda in water. So that's endothermic. All right. Now we have our exothermic reaction. Exothermic then, if endothermic is energy is absorbed, exothermic means energy is released. All right, we are releasing energy, so the system is losing energy to the surroundings, or work is being done by the system. All right, some examples of that. Okay, so we talked about that. We talked about something cold. Let's talk about something like hand warmers, right? Those are an exothermic reaction. You feel it, your hand gets warm, right? You start shaking them or whatever you're supposed to do and they get warm. The other one is like dissolving HCl in water. If you feel this reaction, it is very exothermic. It gives off a ton of heat. In fact, if you're making it for a thermodynamic reaction, you have to make it like the day before so it does not get too hot. So that actually kind of brings us to this formation of a solution. So sometimes our solutions are exothermic when we're making them, and sometimes they're endothermic. And this is based on our solvent interactions and our solute interactions. All right, so if our solute-solute interactions are stronger than our solute-solvent interactions, it would be endothermic, and vice versa. If our solute-solute interactions are weaker than our solute-solvent, then it would be exothermic because those attractions have to be broken. So let's go on to 6.2. We have our energy diagrams. This actually goes right along with what we were just talking about, endothermic and exothermic. And we have 7.3, 267 through 272. Still no homework on this one. All right, the next video will definitely get you some homework. All right, so energy diagrams just like kind of map out the reaction, right, in terms of energy. All right, so we map out the chemical reaction in terms of energy. So let's look at an endothermic reaction first. All right, so we have energy. This is usually in kilojoules. This is our reaction progression. All right, so let's look. Here's our reactants, AB. Here's our products, C. So what we saw last time was we saw that this right here, this little area right here was our E sub A. We saw that in our kinetics chapter. But what we have here is we have our difference in energy. So this heat input is going to be called enthalpy. And since it's input, that means we're adding energy. So enthalpy is positive, or our delta H is positive. We'll see more about that in a video to come a little bit later. So we have a delta H that is positive, and that's because our products are at a higher energy than our reactants. Okay, so let's take a little peek at an exothermic reaction. Boop. All right, so our exothermic reaction, let's kind of compare and contrast there. Notice how here our products are at a lower energy. Energy than our reactants. Oops, there we go. Okay, and so this is heat out, so we're going to have delta H being negative here. I don't know, equal sign or not. So if delta H is negative, that means we have an exothermic reaction because heat or energy is being released. Energy released. Right, and up here, energy is absorbed. All right, so that's the video. See you next time.